Here we go. Record. All right. So last time we talked about trying to somehow cleverly circumvent the algebraic fact that to find the slope of a line, we needed 2 points, right? And the reason we were interested in finding the slope of a line at a single point, where we only had 1 point, was because unlike a secant line, which we talked about, that connects a graph at 2 points, we have the number of points needed, that only gives us the average rate of change of the function. I want to know how fast that graph is changing at that moment in time, at that single point in time, okay? And that turns out to be the slope of the tangent line. And it turns out, again, also that the question that both Newton and Leibniz were trying to answer, what's the instantaneous rate of change of a planet at any moment in its orbit around the sun, and what is the slope of a tangent line of a graph that models some behavior at any given point, is the same question, okay? So let me show you kind of what we could do. And this is where it's built on the idea of a limit, okay? Because we need 2 points, you could say, all right, I'll play your silly 2-point game. Does it charge yours too? It does. Oh, okay. So if you have one of those new calculators and you want to charge it, you can charge it there. All right. So here's what we're going to do. We're going to play your game, Mr. Algebra. We're going to choose the point of interest, the point 1, 2, that I have plotted right there. And we're going to choose another point that's nearby. And the point that I'm going to use is 1.5 f of 1.5. So I'm going to use the point 1, 2. I'll just rewrite that here. And that point. So notice the x value, it's only a half a unit away. So I'll use purple here. Let's come over here to 1.5. 1.5 is kind of where the vertex is. So if I draw that purple line that connects it, let me see if I can move it into position. There we go. I can find the slope of that purple line, no problem, right? Now, just looking at it graphically, I might be content with saying, hey, the slope of that purple line is a decent approximation of the slope of my blue line, right? That's kind of what Galileo had to do. He was trying to find instantaneous rate of change of balls rolling down inclined planes. That's what he was after. But he never was able to figure it out. Empirically, he was able to find the average rate of change, the average velocity of these rolling balls, but it was only between 2 moments in time. So that would be kind of analogous here, 2 different x values. So, of course, we're going to set it up. We're not going to actually compute it because, look, I don't want to have to plug 1.5 in there by hand. Yucky, yucky, gross, gross. So we'll let the calculator do the heavy lifting. Now, here's kind of the rule of using the calculator this year. Before you pick up a calculator to type anything in, you should always, always have that expression or whatever it is you're typing into your calculator already written down on your paper or iPad. You got to do all the processing, all the thinking, all the setting up first, and then the calculator is just that computational tool. That's it. So just to do this, we'll just say, we could either say the average rate of change, average ROC equals, and then I'm going to do f of 1.5 minus f of 1 all over 1.5 minus 1. Okay, what do we call that? Not Dairy Queen, but the, yeah, it does give us the slope. If you want to say this is the slope of the secant line, either one. It's always good to kind of keep the two things equated in your head. The average rate of change is kind of the Newtonian perspective, and then the slope of the secant line that connects 2 points is the Leibnizian perspective. But what I was saying here, we call this the difference quotient, right? The DQ. The DQ is your change in y over change in x, delta y over delta x. That's what you want to show. This is one of those hallmark checkpoints for a college board. If they ever ask you to find the slope of a secant line or the slope of the average rate of change, or you'll see later what we're doing here, if they ever ask you to approximate the slope of a tangent line using data, you have to use 2 points. They expect to see the difference quotient. So even though as you're writing it down, you know, hey, I know 1.5 minus 1 is just 0.5, don't write down just 0.5 in the denominator, because they have to see either a sum or a difference of two quantities being divided, okay? So that's just kind of, I'll emphasize that again. All right, now we go to the calculator. This is where the calculator can really pay off. My function is 3x minus x squared. So since I have to restart mine, let's go to y equals, and I'm going to put 3x minus x squared. I'm going to type it into y1. And now I'm using my calculator in this sense, not as a graphing tool. I'm using my calculator as a number crunching device, and I'm using the y equals as simply a repository for a function that I want to recall on the home screen. So once you double check to make sure it's in there correctly, hit second mode, quit, if you will, and get to the home screen. Now we're going to type in this right here, the difference quotient. So alpha y equals enter, or however you want to get to your horizontal quotient, okay? F of, well, my function is called y1 on my calculator, and I can access it by hitting alpha trace. Alpha trace is right there. Let's select the y1, open parentheses 1.5, close parentheses. Okay? That acknowledges it as f of 1.5. Your calculator will compute it and store it. You don't have to like compute it separately and then write down this ugly decimal right there. Now, f of 1, do we know what f of 1 is? It's 2, right? So if you want to put f of 1 there, you could do alpha trace again of 1, or you could just put 2. But putting alpha trace of 1 kind of reinforces what we're doing. And now 1.5 minus 1, here's where you could just put 0.5. The calculator's not going to dock you points if you just put 0.5, but you know what? I'm going to go ahead and type it into my calculator exactly as it is on my paper / iPad. You know why? It's not my, yeah, I was going to double check. What is it? 1.5 minus 1. Golly, yes, thank you. Good. Y'all are good. I was going to say the reason you want to type it in exactly as it is on your paper is because you can come back and double check, but y'all double check before I said it, right? Because if you don't, if you just put like 0.5 down there, that's what I was thinking in my head, you might mess up. Now, you compare that. Other than I'm calling it F and my calculator calls it Y1, it looks the same, doesn't it? And now you can hit enter, boom. And then you write it down. You can put 0.5 or 1/2, whatever. Okay, so let's think about what we just did. We're trying to find the slope of the blue tangent line because that's going to tell us how fast that parabola is rising at that moment. I had to choose another point that was a ½ unit away, and I got a ½. So the purple slope is a ½, up 1/2. At this point, you might say that means that the blue slope is maybe 1/2, but actually a little bit wider, smaller or bigger? Yeah, greater. It's a little greater than a ½. So 0.5, maybe it's 0.6. Maybe that's my thinking. Now, I'm just going to say it's about 0.6. That's good enough, you know, for the people I hang out with, right? No, I hang out with a pretty stingy class of people. So we want to get a better approximation. Let me just say, my wife would not be content with approximately 0.5. That's insane. Do better, right? I was like, okay, I will. So let's choose another point. We're going to choose the point of interest, which is still the point 1 comma f of 1. And of course, that's the same point as 1 comma 2. Now I'm going to choose that second point to be closer than 1.5. It's 1.1. So I'm going to go ahead and write m for slope. You can put average rate of change again, but now it's going to be f of 1.1 minus f of 1 all over 1.1 minus 1. Difference quotient. Get in the habit of labeling your expressions, okay? You're not going to lose points if your difference quotient just appears, but it's always nice to give it a name. That way it helps you. Average rate of change, slope of the secant line, m for slope. Now we go to the calculator, and you can either type it in again, just fresh from the beginning, or you can hit second enter. Second enter recalls the previous line, or you could go up with your arrow pad and grab it and hit enter. I just like to hit second enter. And then I'm going to come back, and the only thing I'm changing is the 1.5. I'm just going to type on top of it, and I'm going to put a 1. Okay. Again, you double check before you hit enter. We're recalling the answer from Y1, and it should be, there you go, it's 0.9. So this equals 0.9. a word on the equality. Once you do establish an equal sign, I guess I should have put another one here, but I was using the other one. You should keep an equal sign. Once you create an equation, you need to maintain your equation all the way through the work, okay? All right, so let's see what that looked like. That might be kind of harder to draw. I'll use green for it. Maybe 1.1 is about right here, just hypothetically, okay? And so if I were to draw the slope of that line, it's going to come through like this. Or if I were to draw that line, looks something like that. There you go. And so if that's the green slope, let me put it in green, 0.9. I'm like, oh, yeah, okay. That's a better approximation now of the blue slope, isn't it? I was going to say 0.6. I knew it was bigger than 0.5. I didn't know it was all the way to 0.9. So, yeah. Thanks, honey, for bringing out the better in me. I want to bring out the best in you, not the better. Okay. She's going to make me do it again. Dang it. All right. Let me choose a point that's yet closer. How about 1.01? That's only what? 100th of a unit away. And if you're talking about time, that's only 100th of, let's say, a second. That's going to be like, woof, woof. That's almost at an instant, isn't it? Now, I don't know if I could draw that, but maybe we'll try at the end. Let's go ahead and set up the difference quotient. I'm going to choose beefy brown for this one. The slope is f of 1.01 minus f of 1. Again, get in the habit of doing final minus initial. And that's in terms of x, right? The larger x value's function value minus the smaller. If you get in the habit of doing that, then when we get to a particle motion, the numerator becomes displacement. All right, so again, y'all know what to do. Second enter. Let's go back. We're going to change insert. So if you don't want to type it in again, if it's blinking on top of where you want to insert something, all you have to do is hit second delete. And it allows you to type in, whoa, that didn't work. No, that didn't work either. Get out of there. Okay. All you have to do is insert by hitting second, delete, and then type in a 0. Right on top where you want it. Second, delete, and a 0. Okay. Or you can type it in again. Y'all can type faster with your fingers than I can with my stylus here. But again, you double check, you triple check before you hit enter. That's the whole beauty of having math print on your calculator. It should match your math language. Hit enter, and we get, ooh, 0.99. Okay, all right. So, man, the slope of the tangent line, I'm going to put a little brown dot right there. God, you think I could draw it? I don't know. Let's see. There we go. That's not bad. That brown line now is a better approximation of the blue line. And so I can use the brown slope as an approximation of the blue slope. All right. So the instantaneous rate of change, it approximately at x equals 1, the blue line is increasing 0.99 units vertically for every 1 unit it's moving horizontally. That's not bad. That's not bad. Do you see the idea of the limit here? That other point that we're forced to use, that algebra is requiring us to use, it's getting closer and closer and closer. It's approaching the point we want. Now, this is the last one that I'm going to do. I don't know if I'll be able to even draw it on there. I'll try. Let's use red for this. We're going to say the slope is f of 1.001 minus f of 1 all over 1.001 minus 1. That would be like equivalent to 1,000th of a second. Imagine Galileo primitively taking a ball, letting it go down an inclined plane, measuring out its position, and then 1,000th of a second trying to measure its position. Physically impossible, right? This is how empirical science works, though. Okay, so we're kind of using the empirical nature to guide us on these calculations, which will lead us towards a theoretical solution. All right, so typing it in again, second enter, scrolling back. I just need to insert, second delete, 1 more 0 there, and same thing here. 1 more 0, second. Ah, I didn't do that right. Yeah, that's why you're supposed to double check. All right, so right there, second, delete, 0. Now I like to click to the right to get out of there and just compare it. Now it looks good. Okay, so now I see that it's 0.999. All right. What the heck? I'm gonna try to draw that. I don't know if I've ever been successful at doing that. That's right there. So it would have to like come in here and leave there. Oh, that failed. You know, it's got to, it wants to become the blue line. I'm not going to try and draw it. You get the idea, right? So let's look at the data, because the data is really where the reveal is at. Although visually it looks like it's becoming that. Look at part E. Based upon the mathematical evidence above, could we then go out on a limb, if you will, and determine how fast the graph is rising or changing at x equals 1? That is, can we determine what the slope of the tangent line is? What would you say it is? 0.999, 999, 9999, 9999. And that, I mean, arbitrarily close is how close that other point can get, right? Infinitely close. And so I can keep adding nines to the end there. It looks like, it would appear that the limit as that other point, let's call that other point a f of a. This is the other point that we're using, okay? It would appear that the limit as the x value approached a of f of a minus f of 1 over a minus 1, it looked like it was approaching 1, right? That's the limit idea right there. As that second point that we're forced to use gets closer and closer and closer to the one that we want, I can see the writing on the wall, 0.9, 0.99, 0.999. So I'm going to go out on a limb and say, here's what I'm going to say. The slope of f of x at x equals was 1, yeah, at x equals 1 is 1. Okay, it just happens to be the same as the slope. So that blue line is going up 1, right 1, up 1, right 1. Okay, so right there is the basis for the seeds of how calculus cleverly circumvents the fact that we need 2 points. Now, everything that we did up here was still 2 points. It was very tedious. Can you imagine doing this without a calculator? Very tedious. And what we did was very, very specific. It only worked for that function, 3x minus x squared, at that point, x equals 1. If I was interested in finding how fast this graph is changing at, let's say, 2.5, I know it's decreasing, so I know it's a negative number. Man, I would have to do all those tedious calculations all over again, wouldn't I? So this is where calculus comes in cleverly. If we could somehow generalize that process that we did at this point, I think we might be able to extract or distill, if you will, some type of new mathematics. You want to try it? But we don't want to take too big of a step, because we might lose some of the product. So we're just going to take it in baby steps, and that brings us to example 2. All right. On example 2, it says, find the average rate of change now between the points 1, f of 1. That's the point we've been interested in. Well, look what we're going to do. Instead of choosing that other point up here and just calling it a f of a, here's the genius in it. I'm going to define that second x value to be a certain distance h away from the one I want. This h is nothing more than a delta x, okay? But delta x is a cumbersome unit, right? Delta x is 2 variables, really, a delta times an x, that acts as a single unit. So in place of delta x, we replace it with h. You can think of h as being just a hair's width, okay, very thin. So I'm going to find now the slope between these 2 points. And if you want to see what that would look like over here, you could say, of course, then that this is the point 1 comma f of 1. right here. It's the point we're interested in. And then this point over here would be the point 1 plus h, comma, f of 1 plus h. All right? And then how would that translate graphically? Well, if you drop this down to 1, this is now just some arbitrary point, and we're defining the distance here to be h. Sorry, this is h. And h can vary, right? So if you look on example 1, h was 0.5 because we used the point that was a half unit away. On part B, h was 0.1. The second x value is only a tenth of away. On part C, h was 100th, right? On part D, h was 1,000th. So h is the amount of time we let pass between the one we want and the one algebra requires us to use. Does that make sense? And then f of 1 plus h is just the arbitrary function, the function value at the arbitrary point. So let's see what that does. Let's go ahead and find the average rate of change. We're going to set it up algebraically here. The average rate of change, average ROC, or m, or slope of secant line, whatever you want, it's going to be f of 1 plus h minus f of 1 all over 1 plus h minus 1. That's your difference quotient. See that? Yeah. Now, notice what happens in the bottom. What's 1 minus 1? It's 0. So we're really just left with f of 1 plus h minus f of 1 all over h. And that makes sense because remember, this is still your difference quotient. This is the change in y over the change in x. And what did I say h was a single variable representation of? Delta x. Yes.
Instead of average rate of change, should it be a of h?
Oh, yeah, you can write it as a function. We're going to do that on the back end of it. Yeah. He was saying, can we make it a function of h? It will end up being a function of h for sure. But right now, I'm just going to treat it as a variable because you're going to have variables as well up for f of x. Yeah, we'll do that on the back end, Landon. If you remember, though, everybody, this piece right here is what pre-cal had on their first test. They're going to have it again on their second test. They're going to have it again on their third test. In pre-cal, this was what I, and hopefully Mrs. Lincoln and Ms. Skurlock called my favorite problem. I don't know if you remember that. Yeah, and why was it my favorite problem? Well, it's a fantastic problem in and of itself, but it's intimately related to the seeds of calculus. Wow, okay? So let's go ahead and evaluate this. Now that I have it set up, let me move this over so I give myself some room. We can't go to the calculator for this because I have an arbitrary variable h, but I can still evaluate it, right? Because f of, what's my function? My function is f of x. So f of blob equals 3 blob minus blob squared. This is how I'm teaching it to the freshmen. I mean the pre-cal students. Right? Replace x with parentheses. F of whatever's in here goes in here, right? So f of 1, 3, 1, 1, blah, blah, blah. What am I going to plug in? I'm going to plug in a 1 plus h. Yes, yes? So 3 blob minus blob squared. So here we go. This is going to be 3 blob minus blob squared. And if you want, you can show the association, like with brackets. Sometimes that helps. Minus, let me go ahead and plug it in, 1 plus h, 1 plus h. So this 1 plus h here is the same 1 plus h that I plugged in there. Minus, let's put brackets around this. Now we know what f of 1 is, don't we? We calculated that in the very beginning. It's the 0.1 comma 2. So that's just 2. All over h. And it is a function of h already. Sorry, because I'm thinking ahead to the next section where it becomes x. But yeah, this is just a function of h. Now, let's evaluate that. So again, if we work vertically and we run out of room, you just kind of make a new column. New column. All right, so now, once we have it set up, it's kind of the sledgehammer method, isn't it? So let's just kind of expand it out. Equals 3 plus 3h minus. Now, be careful here. We're going to square multiply double square. If you don't know that little trick. to square a binomial, square the first, that gets your first term, multiply these two, and then double it to get the middle term. And then you square the last to get the last term. Because if you FOIL it out, your inner is going to be 1 times h, your outer is going to be 1 times h, and they always double. So square, multiply double, square. Square, multiply double, square. Square, multiply double, square. And we're going to distribute a negative at the same time because we can. So if we square 1, we get 1, and it's minus. Multiply, you get 1h. Double it, you get 2h. Distribute, you get minus 2h. Square the last, you get h squared. Distribute, you get minus h squared. And then we have minus 2. And it's all over h. All right, now here's checkpoint. If you're setting this up correctly, everything in the numerator that doesn't have an h should cancel. And make sure it does. 3 minus 1 minus 2 is in fact 3 minus 3. All right, and we're left with 3h minus 2h, which is 1h, minus h squared over h. Now notice what happens if we let h be 0. Algebraically, what do we get? We get 0 over 0, don't we? If h is 0 and we plug it in here, we get 0 over 0. We should expect that because remember, h is the span between the first point and the second point. And if we let h equal 0, we no longer have 2 points, do we? We're back to the tangent line problem. We're back to 1 point. If you think about that in terms of the Newtonian perspective, h is the span of time that you let go between the first point and the second reading. If h is 0, you haven't let any time elapse. So here's algebra clinging tightly to itself. You can't use 0. If you use 0, you're back to a single point. But you know what? We already have practiced with functions. Is that right? Did I set it up right? Y'all are all squinting like I did something wrong, and that's very possible. Oh, okay. Algebra is clinging to the protection of the 1 point being illegal, right? But algebraically, here's kind of the magic. I just combined like terms up there, yeah. 3h minus 2h is 1h. We can factor out the h, can't we? And that gives us 1 minus h over h. And now, here's the algebraic remedy. They divide out. And we end up with 1 minus h. I'm gonna do a new column for that. That's so profound right there. I'm gonna do, I'm just gonna borrow down here. We're gonna say that it's equal to 1 minus h, comma. Let's warn people not to let 0 be used because it's not in the domain of our function, right, Mendeley? Right. So let's warn people, all right? Now, notice this is a function of h. So on the back end here, as Landon was recommending in the beginning, you can call this average rate of change of h, or a of h for short, or capital C for secant slope of h. Now, here's where, going back to the first example, we should have done this first. I made y'all grab a calculator because the calculations were extremely tedious, but you know what? If we would have been smart about it, we could have done it this way and not even needed a calculator. Because this is the formula that falls off the bone, if you will, when we let that average rate of change just kind of slowly cook on the back burner for several hours. Watch, come back up here. Let's paste that little formula that we have right here. Look on example 1A. I'll use blue. On example 1A, our h was equal to what? When we go from 1 to 1.5, it was 0.5. Well, I'm going to call this a of h because I don't want to write all of that as Landon recommended. Well, what would a of 0.5 be? It would be 1 minus h, which is 1 minus 0.5, which is what? 0.5. Okay. Over here, what was h equal to? From 1 to 1.1, h was 0.1. So what's the average rate of change? Well, it's 1 minus 0.1, which is 0.9. We didn't even need a calculator for that. HA of 0.01 would be 1 minus 0.01, which is 0.99. Oh my gosh, we don't even need a calculator for that. Guys, I'm sorry I made you use a calculator, setting up all these tedious average rates of changes. My bad. Have a great lunch. We'll talk about it afterwards.